We have been looking at equilibrium of bodies, and in the previous lecture we looked at certain elements and what kind of forces do they apply. For example, we looked at smooth surface or rough surface, and we saw that on a particular body a smooth surface applies a normal force, on a particular body a rough surface applies a normal force, as well as it is capable of applying a frictional force. Then we looked at a hinge joint and saw that this can apply force both in the x and the y direction, and we looked at fixed or welded joints, and we saw that this is capable of applying a force in the y, in the x directions, as well as it can create a torque. We had solved examples using this, this and this. Now, let me solve an example using a fixed joint. For this, I take a household example of a gate. Which is on two supports like this. Let the weight of this gate be W, let its width be B, let the distance between the supports be H, and let this distance from the support wall to the point where the gate is supported be A. We want to find the forces that are being applied by the wall on these supports, assuming that the entire weight of the gate is borne by the lower support. So, let us see how the gate is being supported. If I look at the gate, it has a weight pulling it down, then the entire weight is being supported by the lower support. So, it has a force F y pulling it up. In addition, there will be forces in this direction. So, let us call this F x 1 and F x 2. These are the only forces that are there on the gate. Then the equilibrium conditions, that summation F x is 0 gives me F x 1 plus F x 2 is equal to 0, or F x 2 is equal to minus F x 1. Similarly, the condition summation F y is equal to 0 gives me that F y minus W is 0, or F y is equal to W. You may ask at this point, how come these two forces F x 1 and F x 2 are generated? It is because F y and W give a couple in this direction, and to oppose this there must be horizontal forces generated at the joint to counterbalance this couple. So, we have gotten these two answers. Let us now look at balancing the torque. So, I have this gate, here is a force F x 1, and now we have already figured out that there is a force in the opposite direction of the same amount F x 1. They are separated by distance h. Here is a force F y and here is a force W separated by distance b by 2. So, summation tau z is equal to 0 gives me W times b over 2, that is a couple due to F y and W, should be equal to f x 1 times h, or f x 1 is equal to w b over 2 h. So, the forces acting on the gate are W, W, this way W times B over 2 h, and this way W times B over 2 h. These are the net forces acting on the gate. How about the supports themselves? If I look at the support, this is the wall, this is one support, this is the other support. This support, the upper support, is pulling the gate in by a force F x 1, which is W b over 2 h, and therefore, gate must be pulling by Newton's third law the support in this direction with W b over 2 h. Similarly, on the lower support, the gate is being, let us look at the pushed, gate is being pushed this way. So, therefore, there will be a force pushing the support in with a force W b over 2 h. On the lower support, there are more forces. The lower support is providing a vertical force W to the gate, and therefore, there must be a force W pulling it down. Now, we are ready to calculate forces and moments generated on both the supports inside the wall. So, for the upper support, the only force is this way, W b over 2. So, the fixed support is capable of providing another force, W b over 2 h. It will pull it in with the same force W b over 2 h. For the lower support, situation is slightly more complicated. This distance is a, there is a force W down, there is a force W b over 2 h this way. Therefore, at the wall, with respect to this point, there would be a force to balance the vertical force F y. To balance the horizontal force, there will be a force F x, and there will be a torque tau. Let us see what these values are. So, straight away F x is going to come out to be W b over 2 h, F y is going to come out to be W, and the torque is going to come out to be W times A, but not in this direction, because this is the same direction as the W is providing. The direction would be this way. So, this is the torque generated at the support. So, this is one example of how a fixed support is able to support the applied forces from outside, both vertical and horizontal, as well as a torque applied from outside. Having done all this, let me now solve 2 or 3 examples for you from the book of Merriam. As the first problem, let me take, the problem is like this. We have a wheel on a rough surface, and it is touching a roller which is free to move, and it is fixed to the support like this. We apply a torque tau is equal to 60 newtons per meter on the wheel, such that the wheel does not move. We want to find what is the force applied by the wheel on this support. Let me show the support in blue here. We want to calculate the force on this support at this point. The weight of the wheel is some W. You will see it does not really matter. Since the wheel does not move, therefore, it is a static equilibrium problem. There is a torque like this, wheel would have a tendency to rotate in counter clockwise direction, and therefore, there would be a frictional force generated like this. The other force would be provided where the roller is touching the force. What about the direction of this force? Since roller is free to move, there cannot be any force in the horizontal direction like this. If there were a force, this roller would start moving. Therefore, the only force is in the direction perpendicular to the surface and in this direction. We are given that this angle is 30 degrees. So, here is this angle 30 degrees. If we now apply the equilibrium conditions, summation f x is equal to 0 gives us, let this force be n cosine of 30 degrees is equal to f, and therefore, the normal reaction n is going to be f divided by cosine of 30 degrees. Similarly, let me make the picture again. Here is the weight W, here is F, here is normal reaction N, here is the torque tau, this angle is 30 degrees. So, we found that N cosine of 30 degrees is equal to F. Summation F y is equal to 0 would give me, if there is a normal reaction N 2 here, N 2 minus N sin 30 degrees minus W is equal to 0. That is the other condition. And third condition for the torque is summation tau about z is equal to 0. Let me take the torque about the center of the wheel right here shown by blue. If we do that, the torque due to normal reaction N due to this force vanishes. That is the advantage of taking torque about this point, and therefore, I would have F times the radius of the wheel is equal to tau applied, which is 60 newtons per meter, and therefore, F is equal to 60 over r. The radius r is given to be 300 millimeters. Here we will write this in meters. So, this is going to be 60 over 0.3 is equal to 200 newtons. So, we have found that the frictional force to support or the frictional force required so that the wheel does not move even after applying this torque is going to be 200 newtons, and therefore, the normal reaction N near on the roller is going to be 200 divided by cosine of 30 degrees, which you calculate, it comes out to be 231 newtons. So, the force by the roller on the wheel is 231 newtons, and therefore, on the roller there will be a force by the wheel of the same amount 231 newtons, and that is your answer. Let us solve one more problem, and this is, suppose we have a block of wood or steel and it is being clamped by tightening the screws on these two clamps. So, here is one screw A, here is the other screw B, and they are being tightened in opposite directions. They are tightened to the extent that the force on this block on both the directions, the compressive force is of the amount 500 newtons. If this distance is 100 millimeters and this distance is 150 millimeters, we want to find the forces applied by the screws on these clamps, assuming that the forces applied by the screws are in the along the screw direction. So, let us look at the upper clamp. On the upper clamp, there is going to be a force of 500 newtons in the direction opposite to the force it is applying on the block, and the screw would apply a force like this, let us call it A, and the other screw applies a force in the opposite direction, B. You can see right away I made the forces acting in opposite directions, because that is how I would balance the torque and the forces. Since this is essentially a one dimensional problem, I can straight away write F y is equal to 0, and that gives me 500 plus B is equal to A. This distance is 100 millimeters and this is 150 millimeters. Let me now balance torque about this point, the point in the middle where the A screw is. So, tau z is equal to 0 gives me 100 times B is equal to 500 times 150, or B equals 750 newtons, and this implies A is equal to 1250 newtons. That is the other problem. Let me solve one more problem, and that is a problem where we support a big drum this is problem 3 on cylindrical rollers. The radius of the drum is given to be 1800 millimeters. Its weight is given to be 400 times 9.8 newtons, that is, it is a 400 kilogram drum. A man of mass 80 kgs starts walking on the drum, and when he reaches here, which is 700 mm distance from the center, the drum starts moving, just begins to rotate on these rollers A and B. The B roller, these rollers are also cylindrical, is capable of applying a frictional force. Roller B is capable of that is why it is only after the man moves a certain distance that the drum starts rolling. We want to find the reactions on A and reactions on NB. To solve the problem, let us make this drum and see what all forces are acting. There will be a force R A acting here, there will be a force R B acting here. The man is at this distance 700 millimeters. There will be a force of 80 G acting this way, and there is a force of 400 G acting this way. The angles are given to be 30 degrees and 60 degrees here. In addition, since the drum has a tendency to rotate like this, there will be a frictional force, let us call it F, at roller B, which is capable of applying a frictional force. Now, we have written all the possible forces that are there on the drum, and let us now apply our equilibrium conditions. So, if we write summation f x equal to 0, summation f y equal to 0 and summation tau z is equal to 0. If we want to find f, that we can do right away. So, let us first apply the torque equation to find f. For this, let us take the center of the drum as our point about which we take the torque. In that case, the only torques that will be coming into picture would be torque due to this weight and torque due to F. If we do that, we will find that torque equal to 0 gives us 80 G times 700 minus 1800, which is the radius, times F is equal to 0. Notice that I did not divide by 1000 to convert 700 and 1800 into meters, because I am using the same units mm on both the forces, and this gives me force F is equal to 80 times 9.8 times 700 over 1800, which comes out to be 305 newtons. Having determined the frictional force F, it is easy to find R A and R B by taking the force conditions. I will leave that exercise for you, but give you the answer, which comes out to be R A is equal to 3770 newtons and R B comes out to be equal to 2352 newtons. You may have noticed that so far we have been doing problems which are essentially two dimensional. In the sense that we have been looking at equilibrium conditions that f x is equal to 0, summation f y is equal to 0 and summation tau z is equal to 0. So, we have been talking about two force components x and y and one component of the torque, and that is in z direction or the torque about the z axis. Now, let us generalize this to 3 dimensions. In 3 dimensions, obviously, the conditions that summation f vector is equal to 0 becomes summation f x is equal to 0, summation f y is equal to 0 and summation f z is equal to 0. Similarly, the condition that summation tau vector is 0 implies that summation of all the torques along the x axis is 0, summation tau y is 0 and summation tau z is 0. Similarly, now that we are talking about 3 dimensional cases, the engineering elements also now we have to consider in view of 3 dimensionality and see that they can apply forces in all 3 directions. Thus, remember in 2 dimensions there was a hinge or a pin joint which was like this, and it was capable of applying a force in x and y direction. Sometimes they are given as reactionary force R x and R y. In 3 dimensions, a similar joint is called a ball and socket joint, which is nothing but a socket in which a ball fits and it can rotate in any directions. So, a ball and socket joint, let me just now show it just like this, is capable of giving force in x, y and z, all 3 directions. Let me make it like this. Let us say this is the z direction. On a socket joint, it can provide a force in x direction, it can provide a force in y direction, and it can provide a force in z direction. This is the 3 dimensional counterpart of the pin joint or hinge joint of 2 dimensions. Let us solve a problem using this concept. Suppose a person wants to lift a very heavy load, and what he does is digs a hole in the ground and puts a pole in it, a long pole. He hangs the weight somewhere in the middle, let us say at a distance of L1. Let the length of the pole be L, and then he applies forces horizontally by 2 ropes in 2 directions like this. What is the tension in these ropes? That is we want to know, and what are the reactions here in x, y and z directions, n x, n y and n z. So, let us first choose our axis x, y and z. We choose our axis in such a manner that the pole is over the y axis and is in the y z plane. X, y and z. Let the pole be the y z plane over the y axis, making an angle theta from the y axis. The load is at a distance L1 and let the weight be W. The ropes are in the x y plane and let them make each of them an angle of alpha from the y axis. They are in the x y plane. We want to find out the tension in the rope and the forces N x, the force N y and the force N z. At this point, I am making all the forces towards the origin, but it does not matter. So, let us now consider the equations for equilibrium. Summation over f gives summation f x is equal to 0, summation f y is equal to 0 and summation f z is equal to 0. Let us consider forces in all 3 directions. So, let me make the picture again. X, y, z. This is how the pole looks. I am making it slightly tilted. There is a weight W acting downwards. This length is L1. This entire length is L2. There is normal reaction Nx, Ny and Nz, and there are these two tensions in xy plane making angle alpha from here. So, if I were to write the force, let me call this tension 1, let me call this tension 2. T1 vector is nothing but minus T sin alpha I minus T cosine of alpha j, because the tension T1 has component in negative x direction and negative y direction. Similarly, tension T2 is equal to T sin alpha I minus T cosine alpha j. So, these are the two forces arising from the tension. The weight acts in the vertical direction. So, summation f x is equal to 0 gives me minus T sin alpha plus T sin alpha plus n x is equal to 0, or this implies, this cancels, that n x, the normal reaction in x direction, is 0. It does not really matter, actually this should have been negative here. Similarly, summation f y is equal to 0 implies that minus T cosine alpha minus T cosine alpha minus n y is equal to 0, or n y is equal to 2 T cosine of alpha with a minus sign. So, n y has a magnitude of 2 T cosine alpha, and the negative sign in front indicates that it is in the direction opposite to what has been shown in the figure here, going towards the origin. So, n y is actually 2 T cosine alpha j. The third condition, the summation f z is equal to 0 gives minus n z minus w is equal to 0, or n z is equal to minus w, again showing that n z is equal to w and in the direction opposite to what has been shown, and therefore, n z is equal to w times k. So, what we have determined on this rod or on the pole that has been sort of put in a ball in a socket joint is that there is a force on this due to the ground, due to the hole on the ground, which is equal to 2 T cosine of alpha. There is a normal reaction in the z direction which is equal to w. There is a force w pulling it down. There is no force in the x direction, and then there are these two tensions in the x y plane working at an angle alpha like this. This angle is given to be theta. Let us now take the condition summation tau is equal to 0. To calculate tau, let us take the origin to be at the origin of the x y z system O. So, that this comes out to be L1 cosine of theta j plus L1 sine of theta k, that is when L1 is this distance. So, distance where w is acting is L1 cosine theta j plus L1 sine theta k, cross product of minus w k. The other forces are tension. So, that would be plus L cosine of theta j plus L1, L sine of theta k cross. Since the two forces are acting at the same point, I can write the torque for their summation, which would be equal to minus 2 t cosine of alpha j, and this should be equal to 0. This condition would determine the tension T. So, let us work this out. The first term is going to give me j cross k, which is I L1 cosine theta times W. So, first term gives me I minus L1 W cosine theta. The second term again j cross j is 0. So, k cross j is minus I. So, it gives me plus 2 T L cosine alpha sin theta. So, this gives me plus 2 T L cosine alpha sin theta. This is also in I direction and this is equal to 0, and that gives me T is equal to L1 W cosine theta divided by 2 L cosine alpha sine of theta. Once T is calculated, you can calculate N y, which is equal to 2 T cosine of alpha in magnitude, which will come out to be L1 W cosine theta over L sine of theta, and that is your answer. So, we considered a ball and socket joint. Recall now that in 2 dimensions there was also a fixed support or a welded or glued support. Let me just remind you what it was. It was a support that was either built in a wall or it was something that was welded or glued here, and these supports could provide a force in x direction, in y direction, as well as a torque tau. The 3-dimensional generalization of this is going to be again a beam either fixed in a wall or something which is glued or welded at its corners, but now it can provide, given x, y and z directions, and suppose this is the fixed support, it can provide a force in x direction, it can provide a force in y direction, and in addition it can provide a force in z direction. Since it is fixed in the wall, using arguments that we use in say 2 dimensions, it can also provide a torque about the x direction, it can also provide a torque about the y direction, and it can also provide a torque about the z direction. This would come out using arguments that we used earlier for the 2-dimensional case, in that when we pushed a built-in support or fixed support in a wall like this, there was forces generated here, and these provided a torque and a couple and a force. You generalize it to 3 dimensions and you will get the answer that a fixed support in 3 dimensions can provide torques and forces along and about all the 3 axes. Hopefully, by the analysis carried out so far, you would be able to now get an idea of what kind of force and what kind of torque can a new element, engineering element, provide. For example, suppose I were to give you a support like this, with some thickness through which I put a shaft through a hole here. Now, you will see if I rotate the shaft like this, it cannot turn. If I rotate the shaft like this, it cannot turn. So, if I take this to be x, this to be y, and this to be the z direction, let me be little more careful. Let me put y perpendicular to the support like this. Then you can see that about the x axis I cannot rotate it. So, the support gives a tau x. About the z axis I cannot rotate it. So, it gives me tau z. However, I can rotate it about the y axis, and therefore, this kind of support would give me on the shaft a tau x, a tau z, but no tau y. On the other hand, I cannot push it along the x direction, and therefore, it gives me a normal reaction along the x axis. I cannot push it along the y direction if the shaft is fixed. So, it gives me a suppose I could push it along the y direction, then there is no force in this direction, but I cannot push it along the z direction. So, it gives me a force in the z direction. In addition, if it were also fixed along the y axis, if the shaft was completely fixed, then it would also provide a force in y direction. If it was not free to rotate, it will also provide a torque along the y direction. So, you can do analysis like this and find out what all an engineering element, what all kind of forces and torques can it tolerate or provide for equilibrium. Having talked about elements, let me now talk about a few cases of different forces that due to geometry, their particular geometry make certain conditions, equilibrium conditions irrelevant. For example, let us take case 1. All forces intersect at a given point. So, suppose there is a body and all the forces applied, they may not be applied at the same point. So, F1, F2, F3, F4, but they all say intersect at a particular point. Let me show this point here like this. They all intersect at this point. In that case, the condition that torques be 0 becomes irrelevant, because if I can take the torque about, if I take the torque about this point where they intersect, the torque about this point O would be 0 for all the forces, and therefore, the only equilibrium conditions I require are summation f x is equal to 0, summation f y is equal to 0, and summation f z is equal to 0. The forces that intersect at a particular point are known as forces concurrent on a point, forces concurrent at a point. So, for forces concurrent at a point, the only equilibrium condition is summation f x equal to 0, summation f y is equal to 0, and summation f z equal to 0. Let us take a look at another situation in which suppose the forces all intersect a particular line, no matter where they are applied, but they all intersect a particular line, and let us call that line the z axis for convenience. That line can be arbitrarily chosen to be z axis. So, this is force F1, force F2, force F3, force F4, force F5, and they are all intersecting the z axis or a given line at one point or the other. Let us see what happens in this case. In such a case, by the transmissibility of force vector, I can take each force to be acting at point say z I k, that is at a distance z I in the z direction, and therefore, the torque by the forces is going to be summation I z I k cross f I x component I plus f I y component in j direction plus f I z component in k direction. And if I evaluate this, since k cross k is 0, you will see this comes out to be summation I z I f I x, k cross I is j, minus z I f I y, k cross j is I with a minus sign. So, minus sign we have taken care of. So, you see the only component of torques that such forces that are intersecting, all intersecting one particular line which we take to be the z axis, give torques in the direction only x and y, and therefore, we need not worry about the condition that summation tau z is 0. Such forces are called concurrent on a line. So, forces concurrent on a line give me torque tau z equal to 0. So, let us rewrite it. So, we have a situation where all the forces are concurrent on a line, that is they all intersect one particular line which we are taking to be the z axis. In that case, of course, I have to satisfy summation f x is equal to 0, summation f y is equal to 0, summation f z is equal to 0, and summation tau x is equal to 0, summation tau y is equal to 0. There is no equation for tau z because that automatically is 0. So, that is the other situation in which you realize all of a sudden that you realize suddenly that there is no component of torque in the z direction, and therefore, I need not worry about that equation. As a third situation, let us take forces which are all parallel. Since they are all parallel, let us take that direction along which they are acting as the z direction again. So, that all forces f I vector can be written as f I z o. Let us write the unit vector that we have been using f I k. And therefore, if I were to calculate their torque about any given point, the torque which is x I y I j plus z I k cross f I k would give me again x I f I cross k is j with a minus sign plus y I f I j cross k is I. So, this also has components only in x and y directions. So, I need not worry about the z component of the torque. Since there are no components of the force in x and y direction in this case, therefore, I have summation f x is equal to summation f y is equal to 0 automatically satisfied. I need not consider it. So, in this case, when all the forces applied are parallel and we take that parallel direction to be the z direction, in that case the equilibrium condition is going to be summation f z is equal to 0, summation tau x is equal to 0 and summation tau y is equal to 0, only 3 conditions. Of course, if none of these is satisfied, in general we have the condition general. If there are all sorts of forces and all sorts of torques applied, in that case of course we have summation f x is equal to 0, summation f y is equal to 0, summation f z is equal to 0, summation tau x is equal to 0, summation tau y is equal to 0, and summation tau z is equal to 0. That is the most general condition, but what we covered earlier in 3 cases is if the forces are concurrent or they are concurrent on a line or if they are parallel, some of these conditions are automatically satisfied and we need not worry about them. So, to review this equilibrium of rigid bodies, and I emphasize these are rigid bodies because we have not allowed any deformation. What we have done so far is taken a particular body and saw what are the external forces applied on them and what are the forces generated, normal reaction to 1, maybe a torque tau, maybe a force, frictional force F. What are these forces given by various elements by which it is held, and then we did the equilibrium condition, summation F is equal to 0 and summation tau is equal to 0. Such a diagram where the elements which are holding the system, we isolate the system and replace those elements holding the system by the normal reactions of those elements or the torques provided by those elements is known as free body diagram. We have been using free body diagram so far, but I did not use this term. Now, I am introducing it. So, free body diagram is the one where I take the body, isolate it and replace all the engineering elements that are holding it by their respective forces or torques provided. So, in considering the equilibrium body, first thing we do is step number 1, equilibrium. Make a free body diagram by isolating of the system in equilibrium, and 2 apply the conditions summation f is equal to 0 and summation tau is equal to 0 and solve it. So, this is a brief introduction to equilibrium of rigid bodies. In the next lectures, coming lectures, we will be applying this condition to a very special engineering structure called trusses.